Hello and good morning. Thank you for joining this session. My name is Brunmai, and today I'm going to talk to you about my experience through the course Introduction to Autonomous Mobility. This 6 weeks training program at LHPU was a very exciting time, and I'm so happy to be here sharing it with all of you. We all know recent technological advancements have steered growth in favor of autonomous and electric industry. So, as the era of automation is driving towards uh, more comfortable and secure transportation, this course gave us the opportunity to create and drive our own self-driving car. We extracted data points, wrote Python software for different sensor technologies, and navigated our RC car as well as the big autonomous electric vehicle here at LHP by sending it messages via CAN communication. During this course, I was lucky to be in a class with my amazing team, Ranadhir, Mahesh, and Umesh, and to be taught by our wonderful TAs, Lal and Milan. Together, we had a great time brainstorming ideas, solving problems, and collaborating with each other to accomplish our goals. So before we proceed, let me give you a little introduction about myself. I have a master's degree in electrical and computer engineering from Oakland University, Michigan. I also have a year and a half experience working as a software engineer at Tata Consultancy Services India. Throughout my graduate school and professional career, I've developed strong fundamentals and gained hands-on experience working with electrical bench equipment, testing electronic circuits, deploying Python and C softwares on embedded platforms such as microcontrollers, microprocessors, and ADAS sensors. Let me now walk you briefly through what I achieved in this course. So after mounting all the hardware components to create a fully framed RC car and configuring the ROS environment, I started with the HC-SR04 ultrasonic sensor. As you can see in this video, the car was able to steer clear of the obstacles, but it wasn't exactly following the yellow lane. So to overcome this downside of sonar, I used a camera, USB Logitech camera sensor. Using this camera, the car was able to follow the yellow lane as well as stay at the center of the track. The next sensor I used was radar. I used a Perceptin radar sensor to decode radar data into the ROS environment via Quasar CAN interface. So I used JADE 1939 CAN communication protocol to do this. Since any one of these sensor technologies was not sufficient to navigate the car satisfactorily, there was a need to have multiple sensors that could augment each other. To serve the purpose, I used a RP LiDAR that is at the top and a camera and a fusion of these two. So the camera would detect the lane and stay at the center of the track, and the LiDAR would detect any obstacle that comes on the way of the car. And if there's an obstacle, it will stop until the obstacle is removed. But since these sensors were more suitable for indoor use, and in order to navigate the car, the go-kart in the outdoor environments and help it deal with the outdoor parameters, natural parameters such as sunlight and other noises in the background, I had more improved and better resolution sensors such as Velodyne VLP16 LiDAR and Z camera sensor. So the first video here shows the car is in a stationary mode and the steering wheels of the car are rotating as we rotate or as we move the yellow color object. The next video shows how the cart would follow the yellow object, and if there's an obstacle to its right, it would go left. If there's an obstacle on its left, it would go right. And if there's an obstacle at the front, it would stop. The third video shows how if there's an obstacle, it would stop. And if the obstacle is removed, if there's no hindrance ahead of it, it would continue. So to conclude, this program helped me really sharpen my Python programming skills. I wrote, debugged, and tested Python code using different test scenarios and made sure that the code runs correctly. I also familiarized myself with ROS framework using different commands and communicating different publisher and subscriber nodes while sensor fusion. I was able to process, filter, and segment raw data from individual ADAS sensors to navigate the car and give it steering, throttle, and brake commands to change the direction of the car and or the throttle of the car. So this was my learning through the course. My future work is I would be interested in using SLAM tool for localization and mapping. I would like to create a map of the environment and localize the position of my car accordingly. I would also like to implement machine learning and deep neural network algorithms to train the machine to identify the raw data and drive the vehicle. Thank you. That's my part for today. I would now like to ask my colleague Omesh to present his part. Thanks.
Thanks, Mrunmai. Hello all, this is Omesh. I am a graduate mechanical engineer with hands-on experience in industrial robotics, utilizing Python, C, and MATLAB programming. I have also had a chance to work on model-based controls and hardware or model-in-loop testing. And followed with that is my journey at LHP, where I dive into autonomous vehicles. During my master's, I have had a chance to work on a number of projects that deal with mobile robotics, control algorithms, and vision-based ADAS, which are supported with online certifications of the same. With this given training, I feel very confident to say that I can implement sensor fusion algorithms or use CAN communications on an industry level. LHP has provided a great platform to work on an actual autonomous vehicle utilizing software logic, study the hardware with automotive grade sensors. And this has been a great opportunity so far. It is said that for an autonomous vehicle to work, there are 4 important steps: sensing, perception, decision-making, and actuation. Since most of the work focuses on sensing and perception, I'd like to present my work in those terms. The first case scenario is where I have to follow or track this big pathway with a small autonomous vehicle. The logic is to detect the yellow color and keep following the track. As you can see, the first image on the left is what the camera gets to see. The second image in the center shows that the yellow color is correctly calibrated and the black color is the background. And follows is the video where it can be seen that the car successfully and very accurately follows the yellow line. Moving on comes the second case, which is the major case scenario of sensor fusion. This is where I implement camera in fusion with LiDAR. The goal is to follow the line with camera and detect any obstacles in the way using LiDAR. The LiDAR that I use here is a Velodyne LiDAR. It provides a nice 360-degree view of all the measurements of the close-by objects. As you can see in the image on the right, that's the crucial 30-degree view that I need to detect any objects that come in front of it. I'd again like to focus on the camera in this case. I feel that camera is a bit more crucial here because the resolution is very wide. In this case, the camera not only focuses on the lane, but also the building as well as the sky. If a simple color detection or color thresholding is implemented, as you can see on the top right image, there's a lot of noise that gets accumulated. A simple image processing algorithm can then bring us to a result where there is a proper lane detection with all of the black background. And as a result of this, this is the video. The car follows the white line perfectly. And whenever me as an object tries to come within a 2-meter distance of the vehicle stops. And this goes on to complete a loop around the building. So fast forwarding that. This has been most of my work so far. Some of the future things that I'd like to work on is implementing a path planning algorithm and navigating this vehicle using GPS. Some of the things that I did start is detecting cars, in this case, keyboards as well as chairs, utilizing a neural nets provided by NVIDIA. Or in the second picture, creating a map with vision-based SLAM algorithm. And I hope to finish these things sometime soon. That's it for me. Thank you so much. Next, we'll be presenting Ranadhir.
Hello everyone, this is Ranadhir Parvatam. I'm a recent graduate from Michigan Technological University with a master's degree in mechanical engineering. So during my master's degree, while I was at school, I was fortunate to work with Volvo Trucks North America for 1 year as a control system and validation intern, where I worked on ADAS features and testing of both Volvo and Mack trucks. So most of the projects in the master's degree are related to automotive and embedded controls. So the main motive for me to join this course is to understand the hardware architecture and the software development that are used in the sensing and fusing of different ADAS features like lane departure warning, highway departure warning. Like I was furious when I couldn't figure out what is happening behind these technologies while I was testing these technologies at Volvo. So the overview of the vehicle we used here at LSP, so you could see I labeled different sensors, LiDAR, camera, and radar here. So moving on. So this is me testing different ADAS features on a truck. So you could see how we test on road using live data. So here working this technology with live data and sensor fusion. Here are different sensors I've used in the course. Camera. So you could see I used camera for lane detection. You implemented some OpenCV functions where I could see the cart is moving along the center of the lane. The color coding I used here is yellow, so you could see the video here. So the cart moves according to the lane, so it takes turn at the right movement and follows the lane accordingly. So LiDAR, so the second sensor I used is LiDAR. So I used Validane LiDAR, it gives 360-degree range. So it detects the object in the range. So consider me as an object with the yellow holding. So when I enter in the minimum perimeter of the LiDAR range, it detects the object and holds it. So here's the fusion video where I fused camera with LiDAR. So you could see me following left, right, and the vehicle steers accordingly, following me towards left and right. And at the end, when I enter in the LiDAR range, which is 2 meters, it just stops accordingly. So the conclusion, so the main takeaways for me from this course is I just improved my scripting knowledge and the hardware architecture that's used in the sensors. So the main sensors I've used here are camera, LiDAR, radar, and sonar. So using different sensors individually and fusing them together was the fun part of this course. And for coming to the future work, I would like to work with these sensors on different ADAS features and try to implement them in the industry level. Yeah, sure. Thank you. That's me. So from now, my friend Mahesh will go on and present his work. Thank you.
Hello everyone, I am Mahesh. I would like to introduce myself. I am a master's student in automotive systems engineering from University of Michigan Dearborn. I have a work experience related to vehicle modeling and simulation, where I worked in Bosch India Limited. So my research area and my expertise is in vehicle dynamics, vehicle modeling and simulation, and signal processing filter designs. Yeah, and I would like to work on ADAS algorithm development and autonomous vehicle algorithm development in future. So today's outline is I would like to explain about the autonomous vehicles and the sensors, sensor fusion, and my accomplishment and the future scopes. So first coming to the autonomous vehicles, here I used three main sensors, which are LiDAR, stereo camera, and a radar, because these are the very important sensors which can sense the environment and the dynamic systems. So through that, we can take a data which are required to navigate the vehicle or to control the steering and throttle to navigate the vehicle and to reach to the destination points very safely. And so while developing this algorithm, I have assumed three conditions which are like it's no dynamic environment. It's equivalent to, it is assumed as a static object around the ego vehicle, and the testing is on an ambient light and weather condition, and there is no consideration of dynamic and kinematic of the vehicle. So these factors affects algorithm. So we developed based on these assumptions. So let me go through my algorithm development stages. So here, the first algorithm what I developed is to navigate the vehicle through a color code of the lanes. It may be a yellow or white color. So the camera will detect that color and try to navigate through by detecting that one, and that color input can be used to control the steering system of the vehicle. So that is my first loop. So if there is a condition like obstacle between nearer to the vehicle less than 1.5 meters, then I return the algorithm to stop the vehicle. So that's the one part. And the second one, the third one, when the obstacle is obstructing the vehicle in its clear path, so it will take a turn and come back to the path again, and again it will use the camera to navigate. So there are two stages. It will take a left turn if the obstacles are on the right side, take a left turn. If the obstacle are right side, it will take the left turn. So this is a basic algorithm which I developed, and implementation of this algorithm by using the ROS platform. So I use the radar sensors and the stereo camera. So those two will publish their data in the format. Camera will publish in frames, and radar will be sending its messages in CAN message. So those two things are used in decoding modularity of program. So radar CAN message decoding module will decode the CAN message and extract the data which we required. So, and the camera will extract the frames, and it will take the center point of the color code, and it will send to the fusion module. So the fusion module will combine both of the things, and the algorithm will be is implemented in that one, and the required commands will be sent through throttle and steering values to the final CAN message. Through CAN message, and it will navigate the way. It will give the command to the vehicle in different scenarios. So yeah, here what I have, this is the implementation and testing of my algorithm. So I show the first video. So here my vehicle is navigating through the yellow detection. So if there is any obstacle coming nearer to that, it will avoid that and take a turn, and it will again comes to the loop of main loop, which is guided by the color code. So that's the one. And if there is an obstacle nearer to 1.5 meters, it will stop, and I will show that video too. So here I navigated the vehicle to an obstacle, and it would stop near the obstacle. You can see that when it stops. Yeah, it stopped here in the range of 1.5 meters. Yeah. So what is the future scopes using this? So I'm thinking to develop a navigation system for autonomous vehicle using GPU and IMU and combining those data to navigate the vehicle to certain GPS coordinates in a perfect manner. So that's the one. And vehicle motion and trajectory control based on a local path planning module. So this is very important for controlling of a steering system and to navigate or to follow the trajectory which we created using local path planning. And so for advanced vehicle chassis control, to reduce the motion sickness of a passenger, we require like a very responsiveness of the vehicle. So the chassis control comes into play to develop these things. So using these sensors and all, I have gained experience to use those data and to optimize the parameters which are very much required to for reduce the motion sickness one. So next, coming to the controlling part, so development and optimizing the decision making and control of the vehicles is by using machine learning and convolution neural network is very important. So I'm trying to work on those things. So yeah, coming to conclusion, I have gained a hands-on experience using the ROS, writing the script in ROS by using Python programming language. So yeah, this could be used for betterment of the society for developing in future autonomous vehicles. So that's it from my side. Thank you very much.